Hi everyone, my name is Adash Desai, and today I'm going to present to you my final project on machine learning foundations for product managers. Today's topic is about predicting the electrical energy output of a combined cycle power plant. The power plant contains multiple ambient environmental sensors which provide data on temperature, ambient pressure, relative humidity, exhaust vacuum, and we need to predict the net hourly electrical output based on this data, right? So we have 9,568 observations of hourly average ambient readings, and the key output metric is the electrical energy of the power plant. So we're going to approach this project in four steps. First step is the algorithm selection. The second step is to split the data into training and test sets, and validating the approach of having the same model split into model A and model B with different features. And finally, the model evaluation to find out which model works better to solve this problem. So let's get into the algorithm selection. In this course, we've covered various topics such as supervised learning, unsupervised learning, including classification as well as regression supervised learning. We've learned about decision trees, random forests. We've also learned about linear regression, lasso regression, ridge regression. And under unsupervised learning, we've learned about the k-means clustering method in this module. So today, I feel for the problem we have at hand, since we have only four specific features in the data, I feel that linear regression works better for this problem. There is a need for interpretability because we need to understand how the model is trying to correlate the features to the output. We need better accuracy based on the net hourly data from various sensors in the power plant. We need better efficiency for the combined cycle power plant, and we also have low variability of the features. So therefore, due to the low variability and the low feature set available in the test data, we rule out lasso and ridge regression, and we stick with multiple linear regression as an algorithm for this particular problem. So going into the training and test data, as explained, I've got two models. Model A, which with the ambient pressure. The reason why I feel that ambient pressure is something that may not have a significant impact on the output of the model is because the range of the ambient pressure is between 993 millibars to 1033 millibars. Whereas, as you can see, the other data sets, some of them spike from 5 degrees to 25 degrees, the temperature. The exhaust vacuum can go from 37 to 57. The humidity as well goes from 59 to 73 and 84 over here. So compared to the other feature sets, the ambient pressure is fairly stable between 993 and 1033, and therefore I've created a model A with the ambient pressure, and we have a model B without the ambient pressure. So this is the hypothesis that ambient pressure may not have a significant impact. So as you can see also that the training data and the test data has a 80-20 split, which means 80% of the data available, which is 7,653 rows, is for training purposes, and for testing the model in the end, we have 1,915 rows of test data available to us. So with this, what we have also done is we've used the Excel method. The program allows us to use three options: Excel, Python, or Google auto machine learning tools. I have picked Excel for the sake of simplicity since I already had it. So I've used the data tab and enabled data analysis. And based on the data analysis options available, I've selected the regression model. And now let's look at how the output from this is on the next final evaluation slide. So as you can see here on the left, we have the training data results for each model A and model B. On the right side, we've got the test data results for model A and model B. So what I found is that the ambient pressure doesn't really have a significant impact, but there is a a better performance when you include ambient pressure on the fourth decimal of the R square. So if you can see here, the R square is 0.9296 when we have ambient pressure included in the feature set. And without the ambient pressure in the training data, the R square is 0.9293, which is lower. So just for everyone's understanding, when R square is equal to 0, it means that our model cannot explain the variance of the input features. And when the R square is closer to 1, it means that the model is able to explain all the variance and on the input features and better predict the output variable that we want. So, with that said, there's also a correlation with the standard error. You can see that the error is marginally less when there's ambient pressure as well. Whereas, without the ambient pressure, the standard error is 4.54. So, validating this set using the Excel's data analysis for linear regression on model A and training data and model A test data versus the model B training performance and the model B test performance, right? It is very evident and a clear conclusion is here, right? The model A performs better, marginally better in this theoretical problem, but in the real world, when there is more sensory data available and more input data available, this could perform even better in the real world as well, or it may not, based on other features that are available. But in this theoretical project, model A seems to perform better with a higher R square and a lower standard error. So with this, I would like to conclude this project. Thank you for watching my video and thank you for evaluating it. See you again soon. Thank you.